which is very important for the development of unmanned vehicle. Professor Seungkeun Kim did his PhD at the Mechanical and Aerospace Engineering from Seoul National University, which is the best university at Korea, and also his Bachelor of Science from Mechanical and Aerospace Engineering at the same university, Seoul National University. Prof. Kim, time is yours now, Prof. Kim. Please give your lecture. Thank you.
Thank you for your introduction. Can I share my screen now?
Yes, please.
Screen is fine?
Yes, fine, clear, very clear.
Okay. Nice to see you guys. Good morning, everyone in Indonesia. So here is 11 a.m. So the weather is very good in Korea now. So the traditional fall, so 23 Celsius degree. Anyway, today I'm gonna talk about the cooperative mission with the heterogeneous UAVs. So actually, the heterogeneous UAV are two. First one is CTOL. So here, CTOL means the fixed wing aircraft, and then VTOL means the vertical takeoff and landing. It can hover in a designated position. So my aim is to compensate the merits or demerits of each other. So I decided to use this subtitle, Experimental Validation of In-Flight Deployment of a VTOL UAV from a CTOL UAV. So actually, I published a paper about this experiment. So this is a very interesting concept. So I will show you the motivation of this research. So actually, this is not based on the research project. So I did with my students for myself, for self-funding, for fun. So, but I hope, I wish the outcome of this research can be useful for the survival rescue or the close mission to the ground in a far away space. So let me start. So first part is about the background and aim of study. So have you ever seen this type of aircraft? So this is the shuttle carrier aircraft. So my research was inspired by this shuttle carrier aircraft. So actually this Boeing 747 can carry another airplane. Actually, this is the US space shuttle on its back. So as you can see here, the difficulty is more weight to the aircraft and then more drag because of the space shuttle on the back. And then there is a wake to the backward direction to the vertical stabilizer and rudder. And here you can see the traditional vertical stabilizer is in the center of the aircraft, but the two stabilizer went out to the outside of the horizontal stabilizer to avoid the wake from the space shuttle. So actually, this was invented to move the space shuttle. The landed space shuttle in California have to move to the Florida, to the launch site, because the space shuttle was launched in the Florida, but it landed on the desert in California. So there is no way to transport this space shuttle to the launch site. So this is very interesting concept. So nowadays it is not operating anymore, but so I was inspired this kind of concept. If we load the multicopter on the back of the fixed wing UAV, so fixed wing UAV can move to the faraway site with longer endurance, longer flying time. But the multicopter can do some hovering capability to the ground. So it can perform the closer mission to the ground for rescue or something else. So there are two categories for UAVs, the CTOL and VTOL, vertical takeoff and landing, and conventional takeoff and landing. So VTOL actually very efficient for close mission because it has hovering capability, so it can deliver medicine or first aid kit to the survivors or victims. And then there is no need for runways, but it has short coverage and endurance and low wind rejection against the wind disturbance. But CTOL's merit is it can very efficient for wide area mission. So it can have wide coverage and high endurance, and then it has some high wind rejection capability. So if we combine these two types of UAV, we can do the missions close to the ground like this, and here and there. So we can set up some mission with two heterogeneous UAVs cooperation. Okay, here, yeah, there is some SOS signal for faraway space. So can you see the multicopter on the back of the fixed wing? So it can do some integrated takeoff, and then the multicopter can deploy to the backward direction. But there is some problem because it can hit the rudder of the fixed wing UAV. So, and then there is a speed of the fixed wing UAV. So in the initial phase of the deployment, there is the high wind to the multicopters. So there is a high disturbance environment. And then the fixed wing UAV can do the waypoint navigation and its own mission separately. And then the multicopter here can do some search, for example. And then separately, the fixed wing UAV, it can land to the original, the takeoff space. And then the multicopter can do the close mission to the spongeman or the survivors. So that is the concept of operation. Okay, now let's move on to development of real UAV systems for cooperative heterogeneous UAV system. So actually this is the well-known RC aircraft. So Cessna, and length is, and the width is 2 meters, and the weight is 7 kilograms. And then cruise speed is 25 meters per second, and flight duration is 15 minutes. And then this is the very low-cost multicopter here. The weight is just 1 kilogram. And then the length of the diagonal axis is the 50 centimeters. Oh, I'm sorry. Actually, I broke my glasses in the morning.
Oh dear.
I'm so sorry about that. It has been 5 years, but suddenly it broke out this morning when I wipe out my lens. Okay, here this, and then flight duration is shorter than the fixed wing UAV. Yeah, this is the integrated version of the two heterogeneous UAV. Here, there is some mechanical device for restraining and deploying the multicopter here, and then this is fixed wing. Actually, this device, the shape of this device is the wing shape. So the sectional shape is the very similar to the main wing. So it can decrease the drag from the wind. Here. Okay. I will briefly talk about the conventional strategy for the guidance and control of the fixed wing UAV. So actually the load and pitch command coming from the position controller. So I used just the PPID structure for roll and pitch control. And then I used the yaw damper to the rudder channel. And then to track the track between the waypoint, I used the track guidance proposed by us here. This is aerospace science and technology. We proposed the track guidance about to track the linear line or curved line here to follow the track. So we apply the first order differential system. Sorry about that. And then we can control the space constant better is here. So this is very similar to the first order exponential system. So you can converge it to the track line like this by controlling the beta constant. So this is very simple idea. So we applied the guidance of the waypoint tracking. Yeah, this shows the multi-loop control structure for multicopters. So here, X desired, Y desired, and then heading command, and then altitude command. So we designed the PD controller here, or we can use the sliding mode control. And then altitude command is computed from the position and heading command. And then we can finally compute the U1, U2, U3, and U4. So each channel's moment input, and then finally the RPM actuator command can be given to the controller system. So this is the detailed block diagram. So here and there is angle limit and rate change limit. So here is attitude, and this is the angular rate command. So we can switch here. So we can control the quadrotor system attitude in this way. So this is very similar to the PX4 or autopilot structure. So now after the workshop, I will share my presentation. So you can refer to the detailed structure. And then there is difficult to controlling the two UAVs. We need some different types of the ground control system. So we have to do mission planning and control, and we need duplex communication for telemetry and RC channels. So here, our research member, so we need 2 members for emergency RC channels. And then there are 2 ground control systems for telemetry for 2 UAVs. So this is CTOL and VTOL. So firstly, it is integrated as one entity, and then from in-flight deployment, it can be separated. So we need 2 kinds of ground control system. Okay, are you with me? So I'm sorry for my glasses. So
Yes,
now
yes.
let's move. Now
it's
let's
really
move on
interesting,
to
Prof.
Okay, thank you. Now let's move on to the guidance strategy. Yeah, so this is the main part for restoring VTOL attitude just after in-flight deployment. So at that time, there is a high wind because of the speed of the fixed wing UAV. So the multicopter can have some force to the backward direction. So we have to overcome that kind of disturbance environment. So as you can see here, firstly, it can goes up like that. So our strategy is to move to the quadrotor naturally to the backside of the fixed wing UAV, and then we have some safety line here, so it can collide with the rudder here. So we have to avoid the collision with the rudder here. So we designed the trajectory and then operation. So this is flow chart. So normal operation, and then after the deployment, we sense the acceleration. So we detect the launch or free fall detection by using the inertial g-axis acceleration. So the acceleration g gets the lower than -5 meter per sec square. So we decide our multicopter is sliding into the launch or free fall. So we have to restore our attitude. So we have to estimate the attitude and decision on direction on restore the attitude. Here, all there. So we have to decide. So high speed restoration of the attitude. And then we can give very high angular rate command to restore the attitude as soon as possible. And then thrust command. And then finally, we can check the balanced attitude. So if yes, so we can keep the altitude from there. Okay. So altitude hold is successful. We can do more on the additional mission for the multicopter. So this is the flow chart to sense the Euler angle, and then we convert the Euler angle to the quaternion, and then we apply the highlight P and Q command rate controller. So this kind of quaternion angle, we assume the heading is 0. So low and pitch. So what direction is efficient for restoring our attitude, the multicopter's attitude, we have to decide. And then this shows the block diagram of the altitude and attitude. So this is normal attitude and altitude controller, and this is our attitude restoration controller. So recovery controller detect the g-axis acceleration and then generate high angular rate command to restore the attitude. And then PID controller is giving the command to the control mixing block. So normal situation, we are using this switching signal, but after the launch, we can use the switching signals. So this kind of way, we can do some restoration of the attitude. So theta and pi, within this range, we switching the attitude controller. Hold on a second. Give me 5 minutes. Give me 1 minute. I applied the tape, but it is detached. Okay. And then I will show you now the restraint and deployment device. This is very simple concept. Can you see here the movie clip? So we use the simple servo here. So the multicopter can deploy by using this kind of key. So we can rotate the servo arm here. So 90-degree rotation, so we can deploy our VTOL UAV. So this is bottom of VTOL and this is top of CTOL. As you can see here, the shape is airfoil to minimize the drag to the fixed wing UAV. And then with this height, we can avoid the collision to the stabilizer of the fixed wing UAV and then minimize the drag. So our flight test showed that the multicopter has 70% margin with 6 meters per second rise. And then we can restrain the movement of VTOL with 2 columns and servo arm here. Yeah. So now I will show you the interesting movie clips. This is the in-driving deployment test of the VTOL UAV from the on the car. So actually, the driving speed almost 80 km/h. This is very high speed. So from here, as you can see, this kind of a flip is happening to the multicopter, and then it can restore the attitude, our detection. So we decided, okay, let's go to the air. Okay, this is the initial verification. And then now let's move on to the simulations and flight experiment. So we did software in the loop simulation with the flight code. So it took off on the ground and restored attitude from intentional reverse mode at 120 meters here. So here we intentionally reversed the attitude to the 180 degree. So that is perfectly flipped. So multicopter is flipped upside down like this. So from there, our algorithm successfully did the restore the attitude to the 0 degree, to the roll and pitch as well. So in the software, we verified the attitude restoration capability of the proposed algorithm. So as you can see here, goes up, and then the altitude stabilization here. And then this graph shows the roll rate and pitch rate is stabilized as well. So this is just a simulation. And let's move on to the real experiment. So I will hold my glasses. I'm sorry.
It's okay, Prof.
Okay, I will show you once again. So this is very difficult to catch that moment. So here, we flip the attitude intentionally, and after that, the multicopter restore its attitude from the flipping state. So this is we did this kind of flipping by intentional RC control. So from there, automatically can restore its original attitude. But as you can see here, there is some loss of altitude. Okay, this is the logging of the state. This is roll angle, and this is pitch angle. As you can see here, it goes to the 180 degree flipping and then goes back to the original state. So we can restore the attitude by using as I said in the flow chart. So roll rate is stabilized here, and then pitch rate is stabilized as well. So we verified the guidance and control algorithm after the deployment can do well, and then it can perform the attitude restoration. So we decided to go for another experiment. Okay, I will show you this experiment. So our students throw the multicopter in arbitrary attitude. So we did several times of this kind of experiment. So to test the attitude restoration capability, to check from the arbitrary initial condition of the attitude. Okay, I will show you once again. You can see from the YouTube channel so as you can see here, so yeah, this is the captured image. So as you can see here, it is almost flipped and upside down here, and then attitude, restore the attitude and goes up to gain the altitude for safety. So we applied this algorithm. Okay, this is the logged signal of the state. Roll goes to the 180 degree, the perfect flip, and then restore its attitude here. Okay, I will take off my glass. And then pitch angle is stabilized as well, and angular weight as well. And then it goes up to the altitude for safety for our students. And then this is the 2015 Korean robot aircraft competition. So we marked the second. So we challenged real experiment in flight deployment. So here, aircraft is here, and then turn around and coming to the over the runway. So here, yeah, focus on the near the sun. We commanded the separation. Okay. Where is it? Here. Okay. Yeah. It went bad. So it crashed. So we lost our multicopter in 2015 Korean robot aircraft competition. So we challenged it, but probably there is the communication loss between multicopter and ground control station. So probably the attitude restoration algorithm is not activated. So we tried again. So this is the second try. So in the winter, near the winter, we tried. So can you see the multicopter on the back of the fixed wing? So it's very cute. So mother and son. Yeah. So mother is piggybacking the multicopter here, and then turn around, and when it will separate the multicopter in flight. And then the multicopter has to restore its attitude in the air. Okay. Yeah, we did it. Yes. So after the in-flight deployment, the multicopter could restore its attitude and then gain some altitude hold. And then it can do some close mission to the ground. But there is no victims or there is no real risk. But we tested it can do possible collaboration between two UAVs. Okay, let's see. And then after that, the multicopter is doing some automatic waypoint tracking, waypoint navigation. And then now it is switched to the automatic landing. So it is doing automatic landing, and then fixed wing UAV successfully came back to the runway. Yeah. So they took off together but landed separately. So this is the final experiment. So this is the screen. This is captured image. So here there is some high speed from the speed of the fixed wing UAV. It is flipped and then goes to the ground, and then we sense the free fall by using the accelerometer signal, and then we apply the attitude restoration by using the high-speed angular rate command. Okay. Yeah, this is the journal paper published by us last year, experimental study of implied deployment of multicopter from a fixed wing UAV. So you can refer to this paper in detail, the technical contents. So today I showed some movie clips and then experimental result. Yeah, for fun, I will show you another application. Is being done by US company. They are doing some very similar cooperation between fixed wing UAV and multicopter. This is the opposite concept. The fixed wing UAV, the multicopter can catch the fixed wing UAV in the air, and then the multicopter can transport the fixed wing UAV to the air and then launch from the air. So this application means they want to do this kind of things on the ship, because the very small ship does not have any runway for fixed wing UAV. So this company is aiming to develop this kind of the cooperation between fixed wing UAV and multicopter for operation of fixed wing UAV on the ship or very small space. So this is opposite concept to ours. So I introduced this interesting concept introduced by Popular Science. So actually we did first, then these guys. Yeah. So this is conclusions and future work. So by using this concept of cooperative use of heterogeneous UAVs, so longer range and endurance of CTOL UAVs can be used. So we can compensate the weak point of VTOL UAVs, and reversely, a close operation capability to the ground of multicopters can compensate the weak point of the CTOL UAVs. So this is our conclusion, and our future work is to make use of this kind of technique for real applications, but it's underway. Okay, thanks for your attention today. And then let me have questions. Thank you.
Yes, thank you very much, Prof. Kim. It's really interesting presentation. I have some question later. Yeah, it's really very, very interesting because I think 2 months ago we proposed something similar, but for rescue on the water with Mr. Hendro as well, with Prof. Hendro as well, speaker as well at this workshop. Later on, I think we will have a really good discussion later. Okay. Thanks a lot, Prof. Kim. Next, we are having Prof. Erna from the Mathematics department. She is head of the Analysis, Algebra, and Mathematics for Education Laboratory. She did her PhD and master from Bandung Institute of Technology and bachelor degree from Matematika ITS. Prof. Erna will present Kalman Filter application for navigation, guidance, and control. She is expert in the data assimilation, applied analysis, control, and estimation. Prof. Erna, time is yours, Erna. Please.
Thank you. Yeah, thank you, Mr. Subhagan. Good morning, everybody. Good morning, Professor Seungkeun Kim, Pak Hendro, dan Pak Juwari, and all everybody. Thank you very much for the time for me today I will talk about the application of Kalman filter. I will share screen. Oh, it's disabled, still disabled. May I share my screen?
Yes, Bu. Pak Hakam, please allow Prof. Erna to.
Yes.
Okay.
Have you done, Bu Erna?
Okay. Yeah. Thank you. Just minutes. Okay. The title is Kalman Filter Application for Navigation, Guidance, and Control. Actually, this is a part of my research. My big research is about data assimilation. This is the application of Kalman filter. Okay, this is the outline. I will talk about what is Kalman filter algorithm, Kalman filter, the application Kalman filter actually in guidance and control, and concluding remark. Okay, you see here what is Kalman filter. Kalman say that this Kalman filter is a recursion solution to the discrete data for linear filtering problem. This the people who the people propose Kalman filter. The second call Fabis. Kalman filter is a stochastic state observer, and others say that Kalman filter is estimate the state variable and parameter. Another paper say that Kalman filter is a fundamental tool for analysis and solving a broad classing of estimation, and also an optimal minimum mean square error. Actually, Kalman filter is one of data assimilation method. This is the principle of Kalman filter. Suppose we have a linear system here in discrete linear with no stochastic. This is the noise, and also we also have a measurement equation. The principle of Kalman filter is if we want to estimate the state variable based on measurement data set K. Actually, we want to estimate the state variable based on the measurement data. As you know, the measurement data usually is a little, just amount data, not a lot of like state variable. Next. This is the algorithm of Kalman filter. We have initial estimation. There are two steps on Kalman filter. Prediction step is the first step, and the second step is correction step. The first, in the prediction step, we use the model. This is the model. We estimate the state by the model. And after we have the data, measurement, we do some correction. And we do iterative as long we want to estimate. This is modification of Kalman filter. There are some modification. Extended Kalman filter for nonlinear, the ensemble Kalman filter, the unscanned Kalman filter. This is for nonlinear system. The last is the square root covariant filter, reduced rank. This for the linear system. And the new is the iterative ensemble Kalman filter. This just last year is appear, iterative Kalman filter, the new algorithm, I think. Ensemble, unscanted, and extended, that is to for non-linear system to get more accurate estimation, but the square and radius rank, the 4 and 5 into reduce the computation time and for instability numerical. Now we talk about the application Kalman filter, especially for mobile robot. I just one example here. Suppose I have a mobile robot here. This is the angel wheel. This is the angel of position of VS position of a mobile robot. Okay. It will design in this talking, it will design the control such that the mobile robot will pass on the given the trajectory path. The control is designed based on the position estimation of mobile robot. So it's maybe little different with Professor Seungkeun Kim because I designed the controller based on the estimation. The estimation is due by Kalman filter. I'm sorry. Okay. So for Kalman filter, we must have mathematical modeling. Here, this is the mathematical model of mobile robot. The mathematical model can be write in the state space system. The other side, we must have the measurement data. So Kalman filter assimilasi data must have 2 points, the mathematical model like this and the data, measurement data. So in the design the controller, we must do like this. Suppose we have the trajectory part will be past the mobile robot. It's given. This is the desired path. The first time we divide the trajectory part into some segment like this. We divide like this, and we do estimation the position by using Kalman filter or modify Kalman filter. The first, we have the position in the time k minus 1. We estimate the position xk, yk, and vk based on the information xk and xk minus 1 and yk minus 1. After we have the position estimation, we do the controller. How we controller this? We control this, we find the position. What is the position angle of robot? What is the angle of robot wheel? We determine the gradient of desired position. Desired position, the gradient desired position is tangent phi actual yk plus 1 mean yk. This is the estimator. This is the position what we want or desired position. And the angle of robot mobile is inverse tangent of L over phi and the difference of the angle of the body of mobile. And we do continuing the estimation, the position. After that, we give the information about the angle of robot mobile while, and we do again the position. We do continuing step. Okay, this is the algorithm of ensemble, we do by using ensemble Kalman filter. This is the ensemble initial condition, initial estimation. We estimate, this is we call the first time is a prediction step. We do by mathematical model. So we use mathematical model to estimate the position time k. We count, we determine the covariant error, and we find the estimation. After that, we do the correction step. Correction step is based on the measurement data. So after we get the measurement data, we include this to get the better estimation. After we have the estimation at time k, we do again the prediction for time k plus 1. And we do recursively as long we want, never stopping after whatever we want to stop this. Okay, this is some simulation of a mobile robot. Suppose I have a circle trajectory part. The blue is the trajectory part, the real trajectory part, and the red one is the position estimation by Kalman filter. And the second is the other trajectory part. There are a corner here. We just keep this, and like before, the blue is the desired trajectory part, and the red is the estimation of position. As we know, this almost the same. So the robot mobile can follow the trajectory part what we want to the mobile must pass it. Okay, this is the simple example about the controller and estimation Kalman filter for mobile robot. We have another research about the Kalman filter, such as this is the ensemble fuzzy Kalman filter for position estimation autonomous and dynamical system of UV motion. Maybe next time we can collaborate with Professor Seungkeun. I can try to do Kalman filter in his model. Another is estimate control position by using fuzzy Kalman filter method. And the fourth is formation control multi-robot by using extended Kalman filter. And the last is the application robust extended Kalman filter for multi-robot also. It's a concluding remark and further research. So we can see that Kalman filter can be applied to navigation and guidance control robot mobile and also other robot mobile. And we know that for nonlinear system is used the ensemble Kalman filter and unscanned Kalman filter. There are some interesting research about the application Kalman filter. Actually, especially for multi-robot, this we done in this we just done in this time guidance control for multi-robot. The next research we must do interface that is must be built so this algorithm can be applied in the real time and control system. In the last one, maybe I must do working with Dr. Hendro, yeah, Pak Hendro. Maybe we can we can do working together to get interface to build for the robot. Okay, thank you. That is my talk. This is simple talk. Thank you, Prof, for Pak Subhan. This is small talking about the Kalman filter. Maybe we can discuss after this. Thank you very much.
Okay. Thank you very much, Prof. Erna, for really interesting. There are some link between Prof. Kim research and Prof. Erna as well, especially in the navigation, guidance, and control. Hopefully, we have me actually Prof. Erna later with Prof. Kim in the forum group discussion, which is Department of Mathematics and Chungnam National University, and also as well later we have from Mechatronics and Industrial Automation Center also. So we have, in this case, we have quite good communication hopefully in the future for this topic. Okay.
Okay.
Let's continue our workshop with the third presenter, which is Prof. Hendro Nurhadi. He is a CEO at the Mechatronics and Industrial Automation Center at Institut Teknologi 10 November. He has actually a lot of projects, not only in the autonomous system, a lot of, and he has a cooperation, some professional cooperation with many industry as well. And he is the boss of, he is the chair of the ship consortium of in Indonesia. And then he is also working on the, and many things actually. He has a ICAR, which is related to Prof. Erna, and he has chief engineer in the iBoat as well, yeah, Prof. Hendro, yeah. I think I don't want to talk too much for him. And he did his doctoral from Mechanical Engineering, Taiwan University of Science and Technology, and he did his master from University of Applied Science, Siemens Ohm, Fachschule Nuremberg, Germany. If it is I right to pronounce. And I think time is yours, Prof. Hendro.
Thank you, my lovely brother, Professor Sobakan. Good morning, or a little bit afternoon in Korea right now, Professor Seungkeun Kim, and also Professor Erna, my mentor actually in mathematics, Prof. Erna, and other colleagues such as Professor Sobakan, and also Prof. Juwari, our lovely brother also at ITS, and also there are several our professors from ITS also attend in this conference, Prof. Martia and many others, Prof. Diki. Thank you for the opportunity, Prof. Subhan. So let me try to share some materials in this conference, but I think Pak Subhan or Prof. Subhan told you too high about me. I'm just a human being, and together we are just a happy family, and we try to get together to do many things together, to have some fun together. So first of all, let us welcome Professor Seungkeun Kim to Indonesia, even virtually. Welcome to Surabaya, and closely or point wisely, welcome to ITS. This building is a rectorate building of our university. So welcome, Professor Kim. And it is opportunity let me try to introduce you all talk related to how mathematics is getting involved to robotics, mechatronics, automation, or control application. A little bit about me, Nurhadi. Me personally, in charge in Department of Mechanical Industry Engineering of Vocational Faculty at ITS. Our faculty is relatively new compared to other faculty, and our department is actually also relatively new. And now ITS supposed charge me on another place. So we have in Surabaya at ITS Surabaya one center and was established since 2010. We call it as a robotics center in eastern part of ITS estate, and we have totally 4 center of excellence at ITS. One of them is our center for mechatronics and industrial automation. Please allow me to firstly to differentiate the definition or the terminology to mechatronics compared to robotics, compared to automation, and compared to control. This all for definition or terminologies a little bit different, which is mechatronics. We can assume it is a mothership of other 3 terminologies. Mechatronics itself, it's found at the beginning in Japan by automotive industry, and robotics itself in Czechia, it's found by a guy from Czechia. He said that robot is a tool, is a helping aid for human being to perform the job more easy or get simple. And automation is actually how to make our job to be automated, and in principally we just use to kind of value in discrete condition, in discrete domain, supposed to be 0 and 1. And control itself, we can play anything with the control terminology regarding to linear control system or non-linear control system and anything else. So the next, this illustration actually what we daily face. In our center, in robotics center, we consist of 3 parts. The western part, the western area, the western estates of this robotics center, this robotics estate, we call it as a commercialization area. And this center located on this western area of robotics center. The middle center of our robotics center, we call it as a research area. We focus on this area to develop our human capacity and capability, and also the research development. And the eastern part of our robotics center, it is dedicated to our students to explore their hobby, their knowledge, their fun. So if we can see the picture at the top, most of those robots are made by our students who compete on the competition or the contest. And let me show you also the daily applications of robots. Normally we understand that the robots looks like a human being, just like a Ultraman or Iron Man or anything else. But In industrial application, as we see in this slide, that there are many serial manipulators that we can see and can face in the application. And many other applications. If we talk about mathematics for robotics and mechatronics, such as smart building, smart campus, smart city, smart factory, smart farming and agriculture, smart hospital, and anything else. There are many. So in this case, I would like to say to all of you that applied mathematics be the soul actually of robotics and mechatronics. In other way, we can say that mechatronics and robotics with no mathematics, oh no, it is impossible at all. So we can go through now to the main piece of this presentation. It is mathematics for robotics and mechatronics. As in the previous presentation from Professor Kim and also from Professor Erna, there are many actually applications of mathematics for robotics and mechatronics. In the previous, we in the center perform several research and development, such as for UAV, such for the thruster. Thruster is a main propulsion driver for underwater vehicle, and also AUV. It is an autonomous underwater vehicle. We still have a problem for this kind of research and development, specifically on the communications problem. So far, we may only develop the research capacity under 3 or 4 meters under the surface of the water. More than that, then that's like we mentioned before, we still have the problem for that. And also unmanned ground vehicle, such as automobile. In this year, we have a iCar. It is an intelligent car that we developed in this year to be our shuttle transportation car in our campus. And also drone for VTOL, vertical takeoff landing, RLV, remotely operated vehicle, and also such application for military research and development, such as a remote control weapon system. In Indonesia, we have a lot of competition or contest in area of robotics. Contest robots in Indonesia, and also contest robot terbang Indonesia, or Indonesian flying object contest. Thank you for the presentation, Professor Kim. So it is initiate us to propose the new theme for next year competition in aerial unmanned vehicle for launching an auto restore VTOL, eventually or CTOL or opposite way for the topics, one of the topics of the competition for next year. Thank you for the injection idea, injected idea. Okay, I will try to carry you all shortly several research in military area to be introduced. The first is the projectile research. We conduct this research also with the mathematics department, with Prof. Erna, with Prof. Seungkeun, with Prof. Diki, Prof. Martia, Prof. Piono, and many other colleagues from mathematics department. The first subject that we develop is estimation of projectile movement using extended Kalman filter in initial condition of moving aircraft. So I will not like to take you further in this topic. I just try to introduce you on the surface. For many subjects in projectile research that we already perform. In principle, that using mathematical model actually simplify our research instead of using real experiments or real real thing to do in the field. And for the next, probably the last several large research area that we perform together with the mathematics department and also other department at ITS is also design control system on full thruster motion, autonomous surface vehicle. And this research, we continue to be implemented to our project in this year also. We call it iBoat. So other than ICA that we developed in this year, another intelligent vehicle that we developed together, collaborated with all related parties at ITS. We call it iBoat, on intelligent boat. So it is kind of a rescue boat from a mothership. So we developed to be an autonomous unmanned rescue boat. Okay, there are several illustrations that we have, the result that we have from autonomous surface vehicle here. Okay, I will not talk about the detail about the result. I just would like to introduce. For the next is autonomous underwater vehicle that I mentioned before. We already try to empirically to have the evidence and also the intuition way, the classical way, how actually to identify empirically or practically, experimentally, if we have a different kind of materials for the hull of the underwater vehicle, and also the different dimension, different geometry dimensions for several design. We already performed this kind of research and still have many things to be done. Furthermore, we are now, unfortunately, and actually it is also kind of opportunity in the pandemic area. So it is kind of a good idea to say that mathematics play a big role in this pandemic area. So I would like to say that mathematics against COVID-19. So mathematics has also big contribution from our campus to the nation to fight the pandemic, the coronavirus. Okay, the first robot that we developed from robotics area, we call it RISA. It is a robot medical assistant ITS Erlangga, collaborated with the governmental university hospital in also Surabaya. It is a RISA. We continue to develop this kind of robots in several purposes. This tandem RISA robots, I hope that the sound of this video also deliver to you. This robot RISA already delivered to several hospitals in Indonesia. The next robot that we developed other than RISA is Violeta. It is a robot ultraviolet ITS developed together with the Erlangga University. Instead of using disinfectant material that we spray or that we that we would like to sterilize our room, we sorry. Oh, okay. In this case, we use an ultraviolet light to sterilize or to kill all the bacteria. The line of ultraviolet light that we use in this variety robotics is 200 to 300 nanometers of UV light. These violator robots currently is implemented in University Airlangga Hospital in CT scan room or operation room. So this is the second robot that we developed in this pandemic era. Okay. Lastly, current research that we try to develop in this year, there are ICAR and iBoot. It is also many modeling, many mathematics subjects that we are using in this boat of ICAR and iBoot. Okay, this ICAR already done for the first phase, for the first iteration of research for ICAR, but we still have the obligation. Actually, we still have the time to continue development of this ICAR to be developed for the next for the next ICAR. So hopefully in this November we can have more than one ICAR that we will deliver to ITS to be the shuttle car in our campus. The last is an iBoot, an intelligent iBoot that we developed in this year. I hope that will be enough, many kind of subjects of research, and also many industrial collaboration to have some research products, such as an OEE monitoring system based on IoT. It is an overall equipment effectiveness. Okay, this video is supposed to be in the last or the caveat of this presentation, this iBoot that we just launched. Actually, this iBoot several days ago on the Madura street or at one of shipyard of in Madura. So you can see this, that the boat with no people on it, and we still frightened actually launch for the first time this boat that we expect that our boat is not go strugglingly by itself to anywhere. So thank you for the attention. I hope that this presentation may trigger, initiate, or stimulate for all of us to get together, to close together, to have collaboration to develop mechatronics, robotics, automation, and control application. Professor Kim, Professor Erna, Professor Juwari, Professor Seungkeun, Professor Matya, Professor Diki, and also any all of the attendees of this conference. Me personally, representing of our center, welcoming you all to come to our center at the robotics building at ITS to come by, to have a drink, to have a instant noodle maybe, and we may chat together to get the opportunity to develop something together in the next future. Thank you, Professor Seungkeun.
Okay, thank you very much, Prof. Hendro. It was very interesting presentation and really related to Prof. Kim project and also Prof. Erna project, because we have a robotic, mechatronic, and any other unmanned vehicle. Hopefully, I was thinking actually when I proposed with class professor to visit Prof. Hendro Robotic Center with Prof. Kim, but unfortunately because of the COVID, Prof. Kim still in Korea, but we have visited already this time with virtually actually to Robotics Center. I was the secretary of the Robotics Center at 2010 till 2012 came, I was not mistaken. Yeah. Yes, Pak Hendro, yeah. I was there, stay in the robotics center after came back from England, Prof. Kim. Maybe you were still in. Okay. Anyway, we will have meeting later, Prof. Hendro, like a forum discussion group with Prof. Kim regarding cooperation of something in the research or in the project. Maybe in the couple of weeks time, yeah. Okay. Finally, we have Professor Juwari. Actually, it was confusing from the promotion team because Prof. Juwari, it was like Korean, Prof. Kim. It's like Korean actually. You will see soon the face. That's why I mean it was yeah, in the poster it was mistaken. He was a Korean as well in the poster. He did his PhD from University Malaysia, from University Malaysia Pahang. His master and also his doctoral, and he did his bachelor from ITS in the chemical engineering department. Vice Dean at the where is it? I still confusing with the name actually. We call it industrial faculty. Yeah, before. Now industrial system. Why is it?
Industrial technology and system engineering.
Okay, that's all. I couldn't repeat it again anyway. Okay, so Prof. Juwari, the topic on the implementation of MPC, which is model predictive control on chemical process industries, which is slightly different because in this time it is from the other side of the not unmanned or something else, but later on maybe now is we have a lot of things like a sensor to identify chemical thing. Like what I did actually is identify chemical thing from such as a fire or chemical weapon, which is really very, very, very difficult to identify. Then we use unmanned vehicle to identify such a dangerous chemical or biological weapon. Okay, Prof. Juwari, time is yours, Prof. Please.
Okay, thank you, Prof. Seungkeun. Good morning, everybody. Good morning, Kim, Prof. Erna, and all the colleagues of Matematika lecturer. Yeah, I am Juwari from Process System Engineering Laboratory, Chemical Engineering Department of 10 November Institute of Technology. So today I would like to present our recent or our master and PhD program about the MPC controller in chemical industry. So the content of this presentation talk about the background, brief history of MPC controller algorithm, DMC, IMC, and also the companies and product of MPC, MPC model identification, and the last one is summary of implementation MPC in industries. So the background of MPC in chemical industry, yeah. Actually, a chemical industry generally consists of many unit operation, which must be operate on a specific operation conditions such as temperature, pressure, and flow. I think little bit different with others presenter before. if your system has very fast response maybe, but in chemical industries has slow response generally, like temperature very slow, but pressure and flow may be faster, but temperature very slow response. And also the PID controller is widely used in industrial control systems in 1940s, but in 1970s, model-based control were applied to industries as all the controller actually need information from process model. In PID process model is used for tuning. However, not all information from process model are captured by PID algorithm. So the PID controller has no direct knowledge of the process in its algorithm. That's why there are many disadvantages of PID algorithm or PID controller in a chemical industry, because they do not use a process model in their algorithm. Just only use the model for tuning. So, and the use of process model explicitly, such as MPC in controller algorithm, would give a lot of advantages. Yeah, for example, this is a column, distillation column. Typically, control configuration distillation column like this. So this is sorry, I use the laser pointer. So this is the loop of controller for temperature in this column. This is the loop controller for pressure controller, for level controller, for flow controller, etc. So many loop feedback control there. So this is use PID controller. Yeah. Typically or conventionally use a PID controller for each feedback control system. So in the MPC structure has an idea like this: to instead of PID controller, using model predictive control. So from the sensor for flow, pressure, temperature, or level, then input to MPC for PID input to PID, but so many feedback control loop, but for model predictive control, we call as multivariate controller. So all the manipulated or control variable calculated in MPC here. Yeah. And then we optimize or in a plane-wide optimization to get the optimum product or condition. Okay, so the brief history of MPC. So the first we call as LQG or linear quadratic Gaussian model for this MPC, and then the first generation of MPC is actually DMC or IDCOM, DMC dynamic matrix control, and then quadratic dynamic matrix control, and also dynamic matrix or DMC plus for the fourth generation MPC, and so many MPC algorithms there. Yeah, because there are so many model or then optimization algorithm. So the different model, different name of the MPC, and also other MPCs such as IMC or internal model control, GPC, generalized predictive control, and so on. Okay, the first we talk about the DMC, dynamic matrix control. So actually, engineers at Shell Oil develop their own independent MPC technology. in the early 1970s, with initial application 1973. And also Karl Ramaker presented detail of unconstrained multivariable controller as DMC, and also paper in 1980, I think Pratt and Gillette describe application of DMC technology to FCCU. Yeah. Fluid catalytic unit reactor. So primary, usually we have FCCU unit reactor to crack the crude oil. Yeah. In 1980, they use DMC technology here. Yeah. The basic structure of MPC can be shown like here. So the process, and then this is the model, and the model can predict the output of the process, and in the controller calculation we optimize to get the optimum output of controller, mean the input to the process. Yeah. So there are many models, and also prediction, and then also controller calculation. Different model, different calculation, controller or optimization, or different prediction model, then different MPC name. For example, dynamic metric mean the model using the metric. Generalized predictive control may be using the state space model. Might be also the model NN, neural network model, so NN MPC. Might be using transfer function, then the name of MPC will be IMC, internal model control. So in the MPC, we in the controller they has future prediction, and also the past of history trajectory. So from the this model, then we calculated the optimization of the controller here to get the next step on the output of controller, mean the input to the process. If time node is k, then the k plus 1 is what step, something like this. So the optimization objective function j to be minimized, yeah, penalize expected value of secure input to the base u, and the state deviation on the x, yeah, from the origin included spread, and also the input weight metric q and r might be also depend on the tuning or number of manipulated or control variable. I do not talk more about the mathematics. Yeah, I just talk about the implementation of the DMC or IMC in this industries. Yeah. For example, here I use the palm oil column distillation here. Yeah, palm oil column distillation. Yeah. We use the HYSYS simulator. The first one, before we implement the DMC, we have to identify the model. Yeah, for example, on the temperature or coefficient on the fraction of the product, because we want to control or maintain the temperature here, and also the product, yeah, bottom product, and also distillate or upper product. Yeah, so we have 4 models. So here we have to identify the process variable is fraction and also the temperature. So we have to have temperature and a fraction model to predict the controller. Okay, so this is the identification models. Okay, then we implement the DMC here, and compare with PI controller. So this is for the temperature, for example, So DMC control has the better performance than a PI controller here. Okay. Then we go through the IMC, internal model control. So this is also one type of the MDC. So in IMC structure, so this is IMC. GP is transfer function of process, or this is the process. GPM is for the models, and the GC is a controller. Yeah. So if our model exactly the same the process, can be imagined if our model is exactly or perfect models, then here the same output here, same with no disturbance. So with no disturbance, a model is exactly the same the process. Then this one is 0. Then the deviation between process and model will be 0. So then here no signal feedback. Mean that GC can be defined easily. So GC is to be inverse of GP to get precise or accurate Y. So all the response will be the same with our set point. 1 over GP times GP, then 1, right? So Y set point times 1 is Y. This is for the simple thing in the IMC. Okay, based on this principle of IMC, then we can elaborate to another structure and how to tune, etc. So in the closed-loop response IMC, Y actually can be derived like this. If disturbance here, then we get the transfer function. If the set point change, then we have this transfer function. Okay, how to tune the IMC controller? As I talked before, that GC is 1 over GP. But for example, if we have a first order system is K over tau S plus 1. Then the 1 over GP will be tau S plus 1 over 1 over K. So unrealizable. So we have to factorize the model to be GP plus or GPM plus GPM minus. Yeah. So we have to make a filter here, because unrealizable of the GC if we use the 1 over GP only. So GC1 of GC actually will be 1 over GPM minus, with beside the plus time the filter. The filter is like this. Yeah, if we have the higher transfer function, then power by R. So R is the higher order. Okay, we introduce or propose some elaboration of IMC, we call as 2DOF IMC. Why? Because if we are using 1 degree of IMC, it only good in the set point trajectory, but for the rejection disturbance, not very good for this 1 degree of freedom IMC. So we propose the 2 degree of freedom IMC, mean we have GC1 also GC2, right? Yeah. But there are some disadvantage, yeah. The standard IMC very slow response to disturbance, yeah. So GC2 also can be solve the problem. What the history of the 2 degree of freedom IMC? So we can see like this. So the upper picture is 1 degree of freedom IMC, so only has GC1, and this one has GC1 and GC2. So actually the feed forward IMC controller to be 2 degree of freedom IMC. And then how to tune GC1 and also GC2. We use the MPGM, we call it MPGM, yeah, like this. Okay, before MPGM, the tuning to the gravity under nominal model can be derived from the transfer function between output and disturbance. So actually, if we derive the transfer function, we can also derive the transfer function of GC2 also, such as GC1 before. Yeah. However, process model might be inaccurate. So if model very accurate, there's no problem. But in the real plant, there is no model perfect. There is no model perfect. Because model uncertainty comes from several sources. For example, the variation of real parameter affecting to the plant operation, the inherent non-linearity of the processes, the experimental extension of the process, or maybe the mathematical model development, mean that our model not accurate. Yeah. Therefore, tuning to the degree of freedom IMC based on uncertainty need to be developed. So we tune the to the degree of freedom IMC based on model uncertainty. Yeah. One specification that has been frequently used for tuning controller is gain margin. So the use of gain margin specification in the standard to the degree of freedom IMC has several drawbacks. Yeah. Therefore, it is also necessary to develop a new structure that can address the drawback, yeah, on the disadvantage. The features on the advantage of the proposed feedback structure, there is the inaccuracy of process model during disturbance input is incorporated in the structure, and put GC1, GC2 are included in the characteristic equation, then it is sufficient to be applied in the gain margin principle. So we can derive the Y or the response of the process like this, yeah. And the proposed method, we determine the worst case based on the worst case, not nominal. Nominal case mean the steady state case, but the worst case might be the bigger uncertainty or the bigger unmatch between model and also the end process. So we tune based on the worst case, and then specify the parameter of the set point controller GC1 and obtain the parameter of GC2 using GM criteria. So GC1 using MP criteria atau maximum peak, ya, maximum peak criteria. GM is gain margin criteria. So we use the maximum peak here to find out the lambda 1, GC1 mean the lambda 1 parameter. We find out the lambda 1 parameter by using this criteria. So the maximum peak is 1.05. Yeah, this is based on the some researcher suggestion. Okay, and then GC2, yeah, then we find out the lambda 2, yeah, lambda 1 and also lambda 2 actually. Okay, this is the some example for the process, and this is the result of the response for the FOPGT process. So for the information that our process in chemical and industry generally can be presented by FOPGT, first order plus date time. Yeah, plus date time. Date time means that the process has time delay, yeah, or very slow response. Yeah, and also we have implemented this proposed method into the heater process pilot plant in our study. Yeah, this plant installed in our university, UMP, University Malaysia Pahang. We use the MATLAB programming for this implementation using Advantage, yeah, PCI and MATLAB 2009A. Yeah, this is from the model identification, and this is the transfer function of the model, and also the controller GC1, also GC2. This is the result of the air heater process in our pilot plant. Okay. Okay, the next, we just the for this slide, and further we will report for some survey of the MPC application in industry based on a paper by Seungkeun. Yeah. So this in this paper in 2003, I think, very complete survey for the application of MPC in chemical industry. After that, I didn't find more complete from there. Yeah. So there are many companies for the MPC controller like Adirsa, Aspentech, Honeywell, Shell, Invensys, yeah, with the different product name, as I mentioned before, that different model or different optimization or different prediction model, then different product name or different MPC name. Yeah, for example, it's like DMC, but the other PFC, Predictive Functional Control, CON, yeah, hierarchical constraint control, and so on. For nonlinear model, yeah, also has a different product name. Okay, for example, for model identification also has a different strategy or different models. DMC plus using step response, such as in my research before, DMC using the step response to identify the model of the plant. Yeah, but in application, it has some difficulties how to get the step response. Yeah, why? Because it's very difficult. Why? Because the how to maintain the model, to maintain the plant. Yeah, if we introduce the step, we have to maintain all the variable to be stable. Only the manipulated or response variable that we focus on the model direction active. Yeah. So there are many models here, yeah, with the different model identification. And also the algorithm for linear and also for nonlinear MPC. Yeah, there's so many company and many algorithm. Yeah, so maybe for mathematician has new algorithm for MPC. You can use your name here to be the name of MPC, for example. Yeah, this algorithm for nonlinear MPC and implementation MPC in industry. And the summary that might be in the last slide. For example, in refining industry, there are 1,012 200 refining using MPC, yeah, and still increase after now. Yeah. Okay. So the others area, maybe petrochemicals, pulp and paper, mining, food processing, polymer, furnace, and etc. Also still in progress to use the MPC for their controller. And the main issue, I think, the main issue of the MPC controller is correlation between process variable. If you using a single or single feedback controller, mean you only has a single loop. Maybe the single loop affected by other loops and other loops, because in chemical industry, so many loop controller, maybe 100, even a dozen for whole plant, and each loop might be interact, yeah, maybe interact between others. So MPC can solve this problem. Why? Because we have the multivariable controller, mean that all the variable calculate in the algorithm in MPC controller. Okay, this is the references, and thank you for your attention. Okay, thank you, Prof. Seungkeun. Still unmute, Prof. Prof. Seungkeun, still unmute. Now,
okay, yeah, okay.
my mic.
Thank you, Prof. Juwari, for your presentation. Because at this workshop, we have so many mathematicians. So you see that as the title of the workshop is workshop series on applied mathematics and computing sciences. So from chemical, from unmanned vehicle, from mechatronics, there are so many mathematics inside. And what is the background of this subject actually? Actually, is the mathematical system theory. We have the expert here. We have Prof. Erna, Prof. Mardia, Prof. Diki. They are working on this object, on this term of mathematical system. But the need for mathematician is to understand the inside. Let's say on the unmanned vehicle, we have the system as well over there. And as mentioned, Prof. Juwari, in the chemical as well, it is so many system over there, but mostly we don't understand the chemical thing inside. Hopefully the cooperation between us later, we can have some student can do some project on the level bachelor or master. Okay, let me read some question from the participant actually. First of all, I've got one question for Prof. Kim from Mr. Muhammad Sahal. As Prof. Kim mentioned, he has to stabilize the altitude of UAV using PID or MNC controller. How to tune the PID or SMC controller parameter? Prof. Kim?
Yeah, I'm here. Actually, there is some misconception about our controller. So actually, we tried to simulate the SMC and PID both, but in a realistic situation, we apply the PID based on the autopilot, open source autopilot. So we tuned the PID controller by following the normal procedure. So actually the PPID for attitude control of the multicopter is very similar to the other copter and PX4. Yeah, this can be an answer to the question. So actually for realistic flight, we haven't applied the SMC yet.
Okay. Mr. Sahal, do you have you can ask something if you want for Prof. Kim, because we have another question later from other presenter actually. Is it fine, Mr. Sahal? Okay. Anyway, maybe he is on the YouTube side. Maybe I'm not really sure. Okay. The second question actually for Prof. Erna. Kalman, how we identify the sensor noise read, Prof. Erna? The question is from Sam Nang, which is Sam Nang Chi Hang, which is from Korea. No, I'm not really sure. Monggo, Erna, please.
Yeah, okay,
and there is another question. Oh, later on for Pak Hendro actually. Monggo, Erna.
Okay, the question is how identify the sensor noise. Yeah, actually in Kalman filter, usually we never know the noise because noise is small disturbance. It's too small. The noise in Kalman filter is a sum have a zero mean and white noise. So Kalman filter can solve or handle the system with zero mean noise. But if have non-zero, there's another problem. We must transfer to the distributed. I think like this. So the noise is assumed as a Gaussian and zero mean. Thank you. Okay. Thank you, Pak Suhan.
Okay, thank you very much, Prof. Erna, for your answer.
Okay, I think we can discuss by VA or other email. If you have a lot of questions, we can discuss by email. Thank you.
Okay, thank you, Prof. Erna. Okay, on the third question, actually for Prof. Hendro, for the nonlinear system, which algorithm do we use to control the plan, Prof. Hendro? I don't know which nonlinear system in this case, but maybe you notice it, Prof. Hendro. Hendro?
Thank you. Sorry for the background because we're just grinding something to work furthermore. Okay. I will try to capture actually the questions. For the nonlinear system, which algorithm do we use to control the plan? The nonlinear system, the algorithm of the nonlinear system, there are many ways how to determine or how to get the nonlinear transfer function. for our plan. There are many approaches. The simplest way how to get the nonlinear algorithm, the nonlinear transfer function, we may identify each of the device, such as a motor, such as the size or geometrical dimension of our vehicle or the system that we have. So from those parameters, we modelize. We make the model from them. The second way, how to derive the transfer function of the nonlinear system, we may starting from derivation of Newton law. For example, that for 6 degrees of freedom dynamic equation of motion, we may use this kind of approach using the Newton law to have the model for the nonlinear control system. And to control this kind of nonlinear control system, even we try to develop many kind of approach methods to be the controller for our nonlinear model, such as FASI, such as GA, such as a sliding mode control, such as many kind of controls. Usually, for experimentally, for the first time to have the original characteristic of the system that we would like to calibrate or to get the setting of the first configuration, we use the PID controller. Probably those kind of information useful for Mr. Samnang Siang. Okay, thank you.
Yeah, thank you, Hendro. It looks like you have some noise from outside of your room, actually. but we couldn't manage to clear up the noise. Okay, thank you, Prof. Hendro, for your answer. Erna, Prof. Erna, you have 2 questions from Mr. Sahal and also from Mbak atau Bu Sunarsih here. The first question is, for nonlinear system problem, how to model the linear dynamic system? For example, A, B, and C. And for the second one, for the path control, how is Kalman filter as compared to the target path iteration algorithm? Okay. Okay, Prof. Erna, maybe you can answer it, please. Thank you.
Thank you. The second question. For nonlinear system problem, usually we do lineares first. So we find the linear system by using Taylor series, and we get the matrix Jacobi. So matrix A, B, and G is Jacobian matrix from the nonlinear system. If we have a linear system, we can apply Kalman filter. But if we don't do lineares, we also can do modify Kalman filter to estimate the nonlinear system, such as extended Kalman filter or the ensemble Kalman filter or unscanted Kalman filter. There is another method to estimate for nonlinear system. Okay, this is the second question like that. The next, the question from Mrs. Sunarsi, how is Kalman filter is compared target path iteration? Actually, I just find target path iteration. I think it's almost the same, like that Kalman filter in the method for tracking, yeah, Kalman filter for tracking and path iteration. But in Kalman filter, we assume the system have noise, but in the target path iteration, we do noise like that. So it's different, it's like this. But the same is The Kalman Filter estimate the every position, almost the same with the target path iteration. Actually, in Kalman Filter, we estimate the state of stochastic system, and measurement data is necessary to increase the accuracy of estimation result. I don't know in the what we call target path iteration, it necessary to get measurement data or not, but determine every path is almost the same with our algorithm in this case. But the general Kalman filter and the target path iteration is different in generally, but in the robot mobile tracking almost the same. Thank you very much. Thank you, Pak Sufan.
Okay, thank you very much, Prof. Erna, for your answer. Yeah, it's now is Prof. Juwari. You have two questions from Mr. Bunteng, Mr. Sahal. I think Mr. Bunteng, yeah, this one, yeah. How can we choose the optimal weight for matrices Q and R? That's the first question. And the second one, what advantage and disadvantage of MPC compared to PID in the process control? And how to consider to choose DMC or IMC appropriate to the problem? Please, Prof. Juwari.
Okay, thank you, Prof. Seungkeun. So on the first question, the optimal weight metric Q and R. So in DMC, actually there are several parameters that we have to tune. Or for example, the delta interval time, yeah, interval time of the data that we have, that we get from the plan. Usually or normally in rule of thumb, yeah, on the step test response, we divide into 100 point, yeah. But some researchers say about 50 till 70, but maybe generally 100. And then we also has the parameter for the future or prediction horizon and control horizon. Yeah, prediction horizon for the rule of thumb something like a 10, and for the control horizon 5 or 7. So some researcher has a different result, but we have some rule of thumb for kind of a characteristic of the model. So actually the weight Q and R also has the default, maybe the default is 1, but for the different characteristic 0 point something, little bit different. Yeah, but there are many researchers to find out the weighting metric, or how to tune the DMC or MPC controller. So the optimal maybe depend on the type of characteristic of the process. Okay, so and the second question, what advantages and disadvantages MPC compared to PID? Yeah, as I mentioned before, that PID is using one or single loop feedback control, right? Single loop feedback control, and PID do not use process model into their algorithm, so they don't know what the model is. Yeah, they do not include process model in their algorithm. In MPC, yeah, MPC use the model, process model in their algorithm, then it can predict the future. What the future response respond if I introduce the input like this. So MPC can predict. And the other advantage of MPC is multi-variable controller, not single variable like PID, single variable then single loop. For MPC multi-variable then multi-loop. So in MPC controller, all the loop can be calculated simultaneously in their algorithm and optimized to get the best one. Okay, and the third question, the last question.
Okay, sorry. I will say it again.
Yeah, how to consider to choose DMC or IMC? Okay, so in DMC we use dynamic metric. Dynamic metric based on step response point or step response data. So if we has, for example, 4 times 4 or 2 times 2 means 2 process mode, process variable or process controller, and 2 multivariable two process control and 2 manipulated variable, then 2.2 can be included in dynamic metric, right? Dynamic metric. So the size of dynamic metric based on our loop can be used for many loop. Yeah. For IMC controller, there is disadvantage for more size of the loop. Yeah, because in internal model control we use a transfer function. So for more size of the loop or multi-loop, then IMC will be very complicated to derive. So in industry, DMC is very famous, and I ever going to go to the refinery process in Balikpapan in 2005 maybe. They installed the DMC controller there. So like in our presentation also, refinery, so many refinery using a DMC controller for application in their process. Okay, I think enough.
Okay. Thank you. Yeah. Okay. Thank you very much, Prof. Juwari. Hopefully, I mean, some of the question I already mentioned it, and I have one question to Prof. Kim actually. How do you control the fixed wing when you launch the multi? I think it must be something on the fixed wing, Prof. Kim.
Okay, that is simple. Actually, we are intentionally controlling the fixed wing UAV goes up in the altitude channel. So just like a ramp input, so goes up slowly to the altitude higher and higher. And when that mode is activated, we activate the in-flight launch of the multicopter. So they are doing just the altitude increasing mode. So there is no special control mode.
Okay. Okay.
So, yeah. So keeping the altitude rate keeping mode.
Okay. So it is autonomous at that time. So just keeping the altitude, yeah. How to keep the altitude? Controlling the altitude, you mean, yeah?
Yeah, actually altitude rate is
altitude rate. Okay.
Yeah.
Okay. As far as I understand, oh, there are some questions actually from Pak Hendro, which is to whom is it, Pak Hendro?
Okay.
Oh, Pak Sigit, yeah, from Pak Sigit actually. Where they have so many questions. I'm sorry. It's just coming up the question for Prof Kim first actually, from Harry Purnawan. He is our student, Prof Kim.
Okay.
You can read it, yeah. Can you read it from the chat?
Okay, I can read it. So actually, the fixed wing UAV normally separate the longitudinal and lateral directional motion because if we combine that, actually that two modes can be separable and decoupled. So if we design for the longitudinal or lateral directional controller, that is working perfectly. In case of the normal fixed wing, for especially in case of the flying wing type, the delta wing, there is a high coupling between two channels, but in normal fixed wing UAVs, that will be totally okay if we design the separate controllers for longitudinal and lateral directional. So normally we are applying to PPID for each channels, but sometimes we can apply LQR for longitudinal channel to control the combined with the thrust and elevator. So velocity and theta, velocity and pitch angle control can be done together with the LQR controller by state space.
Okay. Okay, the next question is for Pak Hendro actually. You have two questions, Pak Hendro.
Mm-hmm.
Is there still noise in your side? Or already reached?
Yeah. I can see the question. I can get the question. Thank you, Pak Seungkeun. This is from Pak Sigit Pencahayani. Pak Sigit apa Bu Sigit ya? Yeah.
Pak Sigit. He is from ITK.
Oh, from ITK. Thank you for the question. It is a very, very good question. For the first questions, probably Prof. Erna being helpful to add more some information about it. But I try to answer this question. Why did you use the Kalman filter and in KF to compare the estimation of ASV? As far as I know that KF for the linear and in KF is for the nonlinear. Is there any consideration? Yes. Since that we have many designs of the trajectories, such as a strike motion and also maneuver and also some other possibility of trajectory designs, then in this case we try to get a proper methodology, which is a Kalman filter or NKF or any other methodology to have for specifically the trajectory that the vehicle has to go to the path or to the trajectory or to the waypoint. So in this case, actually, we try to determine which method appropriate to each single possibility of the motion. So it is not only Kalman filter and also extended Kalman filter, it is also unscanted Kalman filter and also sliding mode control and any approaches that we try to develop to have the method proportionally and appropriately to some specific design trajectory. What is the purpose? The purpose is actually how to switch the controller when the vehicle will go through to the trajectory that it can switch automatically by itself, that the vehicle supposed to use some certain navigation guidance control approach to this kind of motion. But you're right that the Kalman filter is usually and appropriately applicable or implementable for linear model. So for the straightforward, the linear motion from point A to point B directly, it is easiest way to use the Kalman filter for instead of the extended Kalman filter. And for the second question regarding to the linear regression for the activated balance of autonomous unmanned vehicle, after deriving the regression model, will it be introduced to the Kalman filter immediately? The answer is only yes and no. It's just not necessary directly to introduce to the Kalman filter directly. Once again, it depends on actually the strategy or the consideration that we would like to have. We have to try. We have to get some intuitively approach using several methodologies. Thank you, Pak Subaghan.
Okay, thank you very much, Pak Hendro. Thanks all for participant, especially for the speaker, Professor Seungkeun Kim, Professor Erna Apriliani, Professor Hendro Nurhadi, Professor Juwari. Also here we have Bu Mardia. She is Vice Dean at the Department of at the Faculty of Science and Analytic Data Analytic. I'm sorry, Bu Mar, I don't. Yeah, okay. For the final one, I hope you can open your video for the best picture of you. The moderator, Pak Amirul Hakam, is going to take your picture, even though via virtually. That's our life now. It's really global civil society now, yeah, very global. We don't need to come to ITS, even though from Korea, from Arizona State University, or maybe from other place as well. I couldn't mention one by one. Please, Pak Hakam, you can take a picture of us. You can count it, Pak Hakam.
Okay, Pak. The first screen, please smile, give smile. We have 5 screens, so please smile. Second. The third. Four. Yeah, have done, Mr. Prof.
Okay.
Subhan.
Yeah. Thank you very much, Prof. Seungkeun Kim. Thank you very much, Prof. Erna. Thank you very much, Prof. Hendro. Thank you very much, Prof. Juwari, and all participants. Thank you very much for your attention and support. Please fill in the presents on the link. And I have seen some of ITS alumni here. So many. Oh, yeah. Okay, Bapak Ibu semua, Prof. Kim, I would like to say thank you very much. I'm so sorry for your glasses. So, okay, Bapak Ibu semua, terima kasih atas kehadirannya. Semoga barokah ilmu hari ini. Jaga kesehatan semuanya, ya. Insya Allah kita akan ketemu lagi kalau nggak salah tadi tanggal 28 on the 28th of October. Prof. Kim will present biomimetic flapping wing. He is going to present flapping wing At this time, he present multi-copter fixed wing. Next time, he will have like insect, which is the fly. The wing will be moving like the insect, like the bee, let's say. Yes, Prof Kim, yeah, like bee, Prof Kim, yeah. And it's quite difficult for the mechanic thing, I believe, and it will be quite interesting. Yeah. Okay, Bapak Ibu semua. Okay, everyone. Thank you very much for your attention. Mohon maaf kalau I'm so sorry if at this time the moderator make a lot of mistake. Sorry with my English as well. It's Indonesian or Javanese English, not Korean English, Prof Kim ya. And we have interesting actually. Hope to see you again next month or next week as well at the other guest lecturer from Mathematics Department. Thank you. I would like to close again. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Terima kasih.
Thank you, Pak Hendro.
Terima kasih, Pak Hendro.
Okay.